This is the final video in the gases chemistry unit. It is titled Quantitative Gas Chemistry Analysis, and this is focused on the second learning target in the unit. As you can see from the subtarget, some of this stuff we've already been doing, especially gases 2A and 2B. We've been converting between units of pressure, and we've done gas law problems involving before and after scenarios. We will review those gas laws and the problems here as well. The new stuff from this lesson will be gases 2C and 2D, using what we call Avogadro's principle to define and use the molar volume of gases, and then using the ideal gas law, which you already got a look at in the lab from yesterday for calculations and derivations. Alright, reviewing the gas laws. This is stuff that we've already been working with for a few days. We know that volume is inversely proportional to a pressure whenever we have a fixed amount of gas. This is called Boyle's law. Do recall that you don't really need to know that. Not too concerned about matching names up with these relationships. We know that temperature is directly proportional to volume, temperature is directly proportional to pressure at constant volume. This is known as Gay-Lussac's law, and temperature is directly proportional to volume with constant pressure, which is known as Charles' law. And for all of these, we have a fixed amount of gas, and it's non-specific. We don't really even need to know how much gas we have. We just know we have some gas in a container. We change something about the gas, its temperature, its pressure, its volume, one of those three, maybe two of those three, and then we find the new value of the other quantity. Which leads us to using the combined gas law, which is really just all three of these relationships put together, where P1 V1 over T1 is equal to P2 V2 over T2. In other words, we use this for what we refer to as before and after problems. We have one scenario, one set of data for a gas, we change something, and then we have a new set of data that we can find an unknown for. So which leads us to what we call Avogadro's principle. This Avogadro's principle comes from the same Avogadro that we have Avogadro's number for. This idea and research was done by the same guy, Amedeo Avogadro. And I just want you to picture this. Say we had three balloons, all the exact same volume, but the three balloons are filled with three different gases. One of them is filled with hydrogen gas, one's filled with nitrogen gas, one is filled with oxygen gas. I want you to ask yourself, if those three balloons have the same volume and they're at the same temperature and pressure, what do you think that tells us about the amount of gas in the balloons? One initial thought you might have had would be that they should have the same amount of gas because they're the same volume, same temperature, same pressure. And actually, you would be thinking correctly there. Another thought you might have had would be, well, maybe they should be the same amount, but these particles that make them up, they're different sizes. For example, the oxygen molecules here would be actually smaller than a nitrogen molecule, but the hydrogen is actually the smallest one. It's the smallest atom there. So you might be thinking, well, maybe the hydrogen has to contain more particles because it's a smaller molecule. It's a smaller particle. So for it to take up the same volume, you need more of it. Well, Avogadro, in thinking about this, thinking about how tiny all these particles are and how much space there is between them, he came to the realization that as long as we have equal temperatures and equal pressures, that if we have the equal volumes of gases, that they will contain the same number of particles, in other words, the same amount, regardless of how big the particle is. So even though hydrogen molecules are smaller than either nitrogen or oxygen, and oxygen molecules are smaller than nitrogen molecules, even though that's the case, if these gases are occupying the same volume, if they're at the same temperature and pressure, then there will be the same number of particles, or you can think of it the same number of moles of each gas in each balloon. And this really just goes back to what we've learned with the kinetic molecular theory. Recall that for gases, most of a volume of a gas is actually empty space. where these particles are so tiny, there's so much room between them relative to their particle size that it really doesn't matter if one particle is bigger than another. Because these particles take up so little of the volume that a gas occupies, that if you have the same number of particles at the same temperature and pressure, they will have the same volume. In other words, what we can say is if we can come up with what we call a molar volume for a gas, given 1 mole of a gas. So if we have 1 mole of a gas, remember that would be Avogadro's number of particles, 6 times 10 to the 23rd. If that gas is at standard temperature and pressure, regardless of what the gas is, doesn't matter if it's hydrogen, nitrogen, oxygen, you can pick any gas you want to, it will occupy the same volume, and that volume is about 22.4 liters. You can see it here more precisely, 22.414 liters. Again, this is known as the molar volume of a gas. We've been working with molar masses for most of the year. We know a molar mass is the mass of 1 mole of a substance. Well, a molar volume would simply be the volume of 1 mole of a substance. Now, for gases, because of Avogadro's principle, that molar volume is the same for all of them. If we're at STP, 22.414 liters. Now, do note, if we're not at STP, if the temperature and or the pressure changes, then this molar volume would change accordingly. In other words, what we're saying in all of this is that Avogadro's principle tells us that volume is directly proportional to the number of moles. If we were to double the number of moles of gas, and recall that the lowercase letter n represents number of moles, if we were to double the number of moles of gas in a container, as long as the temperature in that container stayed constant and the pressure stayed constant, then the volume of the container would have to double. Or if we were to divide the number of moles by 3, then the volume would have to be divided by 3. If we combine all of these relationships, Avogadro's principle, Boyle's law, Charles' law, Gay-Lussac's law, and we combine all these relationships, we would get this. We would see that the ratio of pressure times volume over the number of moles times the temperature is equal to a constant. And that constant, we give this symbol R. That's the universal gas constant. If we solve this equation differently, essentially if we just multiply both sides by nt to get it out of the denominator, get it over here in the numerator, we get this equation, PV equals nRT, again where P is pressure, V is volume, N is the number of moles, T is temperature, and R is that gas constant, which has the following value. You'll see there are 3 different numbers here. They're all the same value though. The only thing different about them is there's a different pressure unit for each of those numbers you see there. You do not need to memorize these constants. I will always give them to you, but just recognize that you want to choose the one that has the pressure unit in it that you want for the problem. So you can see, for example, this first one is in liter atmosphere per mole Kelvin. The next one's in liters millimeters of mercury per mole Kelvin. And then we have one in liter kilopascals per mole Kelvin. So looking at our learning targets here, we've looked at Avogadro's principle and we've defined the molar volume so we could use that to convert between moles and volume if we wanted to. Next thing we want to do is we want to be able to look at how we use the ideal gas law in calculations, which you've kind of already gotten a start on with the molar mass of butane determination lab that we just did. Let's just go ahead and look at a problem here that deals with the ideal gas law. So here we're asked to determine the Celsius temperature at which 1.25 grams of hydrogen gas will exert a pressure of 2.65 atmospheres when it occupies a volume of 5.60 liters. So the fact that we're asked about a specific amount of gas, in this case the 1.25 grams of hydrogen, we know specifically how much gas we have, and there is no before and after scenario. There is no the hydrogen occupies this volume and has this pressure, and then we change the volume, find what the new pressure is. We're not asked anything like that. This is just a standalone specific amount of gas. That tells you there you're going to use the ideal gas law. So as we go through each of the things we're asked here or told, we're asked to find the temperature. So temperature is equal to, at this point, a question mark. We're given the mass of the gas. We're told we have 1.25 grams. And do remember hydrogen's diatomic, so that would be H2. We know the pressure it exerts of 2.65 atmospheres, and we know the volume that it's occupying, 5.60 liters. So as we just discussed, that tells us we're going to use the ideal gas law, PV equals nRT, because we are given a specific amount of gas, and it's not a before and after. It's not this situation and then a new one. So ask yourself, what are we going to solve for here? And you can see from the variables we listed that we're going to solve for temperature. So just solving this equation for temperature, I need to divide both sides by nR. So that would give me temperature equals PV over nR. If you look at the quantities we have here, we know the pressure, we know the volume. R is a constant, so we always know that. But we're not given N. We're not given the number of moles. Do notice, though, that we are given the mass. So the first thing we need to do here is we need to convert that mass we're given into moles. Well, that's just a mass to moles conversion that we've been doing for quite some time now. We know we can just use the molar mass as a conversion factor. So the molar mass of hydrogen is 2.02 grams per mole. And notice our grams cancel, leaving us in moles. So we have 0.223 moles of hydrogen. So that's what we'll use here for the number of moles in our problem. So just plugging in the values, the pressure that exerts 2.65 atmospheres times the volume of 5.6 liters divided by, again, N is the number of moles. That's what we just calculated here. And then the R value we use is the one that has atmospheres in it, because we're going to need to cancel with our pressure unit atmospheres. So speaking of canceling units, take a look at what cancels here. Atmospheres is going to cancel. Liters will cancel, as will moles. And we're left in Kelvin, which makes perfect sense because we are asked to find the temperature. And as we know, our gas calculations must always be done in Kelvin. Even though we are asked for the Celsius temperature, we'll first get a Kelvin temperature. So if you plug all that in, you'll get 811 Kelvin. And then converting it to Celsius, remember subtracting your 273.15, that will give you 538 degrees Celsius. So the moral of the story here is that we use the ideal gas law when we have a specific amount of gas. Whether that means we're told the mass of it, the number of moles of it, how many particles we have. Anytime that is given and there's no before and after scenario, you're going to use the ideal gas law. I don't have any other example problems on here just because at this point it just turns into math problems because we know we're going to use this. We just want to be able to recognize anytime we have this scenario, you're going to use the ideal gas law, solve it for what you're looking for, and you'll be able to solve the problem pretty easily that way. So looking at a different problem here, we're asked to determine the pressure of an ideal gas that it exerts when it occupies a volume of 218.2 milliliters at 50.5 degrees Celsius if the same amount of gas exerts a pressure of 225 millimeters of mercury when it occupies a volume of 0.3550 liters at 23.4 degrees Celsius. So notice the difference in this problem compared to the last one. We're not given a specific amount of gas, and we have a before and after. So that tells you it's going to be using the combined gas law. Just listing everything that we are given here, we're asked to find P1, and actually you can see I already have the answer down here. Apparently I failed to animate that to have it show up last. We're asked to find the pressure, and we know at that pressure we're looking for, it occupies a volume of 218.2 milliliters, and its temperature is 50.5 degrees Celsius. And we're also told that if it exerts a pressure of 225 millimeters of mercury, so I'll call that P2 because it's a different scenario, it has a volume of 0.355 liters, and its temperature is 23.4 degrees Celsius. So this is a before and after problem, so we're going to want to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. So we're solving for P1, trying to get P1 by itself. So I need to get V1 and T1 to the other side. So you can probably see here we're going to multiply by the reciprocal. So T1 over V1. If I multiply that by that reciprocal, that will give me P1 equals P2 V2 T1 over T2 V1. And now it's just a matter of plugging in some values. Do note our units here. We're going to need to do some conversions. We know we need Kelvin, not Celsius temperatures. Also notice the volume units need to match. I can't put one of them in milliliters, the other one in liters. So you have to convert one of them to the other. It makes no difference which one you do. Just need them to be the same. So when we plug that stuff in, you can see our values here. I chose to convert my volumes into liters, and then my temperatures I have converted into Kelvin. My units canceling, liters cancel, Kelvin cancels. I'm left with millimeters of mercury, which makes sense if we're finding a pressure. And if you plug all that in, you will get 399 millimeters of mercury. So the moral of the story here is we want to use the combined gas law whenever we have a before and after scenario. A specific amount of gas, it could be given. For example, in this problem, we could have been told there's 0.75 moles of the gas. That wouldn't have mattered in how we solved the problem, though, because it's a before and after, and that amount wasn't changing. So it makes no difference if you're given a specific amount if you have these before and after scenarios. So looking at our learning targets here, the sub-targets here for gases 2, we've been converting between gas units. We know how to do before and after problems. We looked at Avogadro's principle here, the fact that equal volumes of gases will contain the same number of particles if they have the same temperature and pressure. And then we saw an example of using the ideal gas law, and hopefully more importantly, we recognized when we need to use that ideal gas law.